Okay, thank you very much, Thelma, for inviting me to give a talk here. As you just mentioned, this is my second time speaking to you here. I'm speaking from Ottawa in Canada. And thank you for all the people taking part, the audience members, both online and in the seminar room. So I'm going to be talking about mathematical modeling and simulations of atmospheric gravity waves. So I'm a mathematician, an applied mathematician, but my work involves geophysical fluid dynamics. As Tama mentioned, different types of, I studied different types of waves in the atmosphere. Last year, I think I talked about vortex Rossby waves, but today I'll focus on internal gravity waves. And I'll just go over a bit of background, basic material, because I'm assuming I'm talking to a somewhat general audience of maybe math people as well as maybe atmospheric sciences people as well. So I'll just start with a few slides which actually overlap the same, very similar to what I presented last year. I don't know if anyone would remember from last year, but I'm going to go over some basic overview just to make sure we are all on the same page. And I expect the audience also includes both students and faculty members and so on. So just try to make it as general as possible. So as I just mentioned, my research interests are in geophysical fluid dynamics. So of course, geophysical involves the physics of the earth, fluid dynamics, so gases and liquids, and which in my context are air and water, air in the atmosphere, water in the oceans and elsewhere, and dynamics, of course, meaning the movement of fluids. Now, of course, the fluids that I study in the atmosphere could be gases or liquids. As we can see in my picture here, this picture was taken in December in Ottawa. This is Dow's Lake, a small kind of lake in the central part of the city. And this was taken in December. We had a bit of snow on the ground, so that's water in solid form. And there's a bit of ice and water over here in the lake. And then, of course, we are interested in things that go on in the atmosphere as well, which includes air, but also water, water vapor, and different gases. So geophysical fluid dynamics is how describes how the atmosphere and oceans and other large bodies of water change with time over the short term and over the long term. So of course, short-term changes describe weather, and long-term changes describe climate. Now, I'm not a meteorologist, so I'm not actually trying to predict the weather or climate, but I'm looking at the mathematics, I'm using mathematics to look at the physical processes and the dynamics that take place in the atmosphere, and with a goal of trying to understand the mechanisms for the different processes, focusing on wave dynamics and how they might affect weather and climate, and how we could get some insights. The goal to get insights that would help us with modeling in using large-scale models. So as an applied mathematician, I'm studying waves in atmospheric flows, of course, from a mathematical perspective, modeling using partial differential equations. And of course, my equations are the usual equations that are used for studying fluid dynamics. So based on the laws of physics, the laws of conservation of mass, momentum, and energy. And so, for example, for conservation of momentum, Newton's second law, which says the force is equal to the mass times the acceleration. And if we write that as a force per unit volume, then it's the mass over the volume, which is the density, times the velocity, times the acceleration, which is the rate of change with time of the velocity, and that gives us equations, derivatives like that. So that's just an example for anyone who's not familiar with the partial differential equations that model fluid dynamics. The density times the acceleration terms gives us our force per unit volume, and I'll be denoting density by rho and the volume by V, and so on. And so written out as partial differential equations in a 3D configuration. Now, of course, if we are studying things that go on our spherical Earth, in the environment of our spherical Earth, ideally we should be using spherical coordinates, but depending on what we are studying and the scale, physical, spatial scales on which the phenomena that we are of interest might occur, we can sometimes approximate by rectangular geometry. But if we are on a small enough region on our spherical domain, oops, when the globe goes in front of my face, then my face disappears. It disappears into the background. So if we are studying something that's taking place on a small enough scale, then we can sometimes use rectangular coordinates. So for example, here in 3D space, if we use rectangular Cartesian coordinates, the usual X, Y, and Z with velocity components U, V, and W, then our equations for the conservation of momentum become density times the acceleration term equal to the sum of any forces acting in our fluid in the region of interest. The density, the rate of change of the velocity component is defined in terms of this big D dt, which is the rate of change following the movement of the fluid with velocity components u, v, w. So we end up with derivatives with respect to the spatial variables and time. And on the right-hand side, we'd have any forces present. Now, in the geophysical context, the forces that we might use in our model will depend on what we are interested in. For example, if we want to study large-scale planetary waves, then certainly the effect of the Coriolis or the influence of the Coriolis force would be important and would need to be included. On a smaller scale, we might be able to omit the effect in our equation if we want a simplified model, just because we are on a small enough scale that we don't, the Coriolis force is relatively small compared with other forces. For gravity waves, we'll need a gravitational force, certainly. There could be pressure gradient forces, and so on. So we'll have our equations for conservation of momentum, as well as equations for mass conservation that we call the continuity equation, and for energy conservation. And so these will give us PDEs representing the rates of change of the properties of the fluid with respect to space and time. And we would study the PDEs in the context of an initial boundary value problem. So some initial state given at time t equal to 0 in some specified region with some information, boundary conditions, which give us some information about the flow at the boundaries of our region. And then we solve our equations in the domain of t greater than 0, using the initial conditions and the boundary conditions. And we might use numerical methods as done in weather forecasting and climate models. Or in the work that I'm doing, I would also use analytical methods, but in order to do so, I would usually have to simplify the equations because we don't have exact solutions for the full Navier-Stokes equations, the equations I showed on the previous slide. So we usually have to make some simplifications, but we can carefully analyze the problem that we are studying and decide which terms we can neglect or what simplifications we can make to make the problem tractable to analytical methods. Now, I'm interested in using I do use both analytical and numerical methods. Usually I start with the analyses to get some understanding of a simplified problem, then put back in terms or put back in the effects I neglected and use numerical methods, using the results of my analyses to verify that the numerics make sense, the numerical results make sense. And so generally results from the analyses can be used for verifying numerical results and also for interpreting information from observations and measurements. And in this talk, I'm going to be talking about gravity waves. So I'm interested in gravity waves in geophysical fluid flows. Now, what are gravity waves? So gravity waves, as the name suggests, are oscillations that result from the effects of the gravitational force combined with the effect of the buoyancy force. Now, the buoyancy force is what allows objects to float, and the gravitational force acts downwards, like downwards meaning towards the Earth. So the balance between the downward gravitational force and the upward buoyancy forces can result in oscillations, which we call gravity waves. And these can occur in situations like what we see in this picture, where there's flow over this may be some water flowing over some bump on the seabed, and that forces fluid particles to go up. But then the buoyancy force would make them float up, but the gravitational force is pushing them down, and so an oscillation can result. So that's what we see in this diagram. Now, gravity waves in geophysical fluid flows, as I mentioned, they result from the gravitational and buoyancy forces. And when they occur in geophysical flows, they are relatively small scale. So what I mean by relatively small scale is relative to the planetary scale. Relative to the circumference of the Earth. And there are different types of gravity waves. In particular, there are surface gravity waves, which occur on the surface of some fluid. So basically are the interface between two fluids. So these are the waves that we see on the ocean surface or at the beach, on the surface of any large body of water. I'm calling it an interface because we've got the air above and the water below. So those are surface gravity waves. And then there are internal gravity waves that would occur in the interior of a fluid. So within the atmosphere or within the ocean or within the water. And we sometimes see them or see structures that look like waves in the clouds. So for example, in this picture here, and also the one, this picture is the same one I have in my background. This when I'm out and I see interesting structures in the clouds, I often take pictures. So this is an example somewhere in Ottawa of the wave-like structures in the clouds. We can kind of see they look similar to the waves that we have here on the surface of the water. This is not the ocean. This is just the beach. The closest we have to a beach in Ottawa, which is connected to the lake shown in the other picture. There's a river connected to the lake, and there's a small beach on the side of the river, on the riverbank. So here's an example taken from the NASA website of gravity wave features over marine stratocumulus clouds over the Indian Ocean. These are pictures taken from above, and you can see the troughs and the crests of the waves in this region, similar to my pictures, to my background picture, and also similar to this other picture here, which is my photo of waves, wave-like structures in the clouds over the Central Experimental Farm here in Ottawa. So just to show that there are different types of waves in the atmosphere. So I'm going to talk about internal gravity waves today, but there are also other planetary scale waves, and there are even smaller scale waves such as vortex Rossby waves that I talked about last time. In this diagram, this is the Earth going from the South Pole to the North Pole, and the equator here, shown in rectangular geometry, and this is the altitude. In the tropics, there are the convection in the tropics is generating different types of waves. There are planetary scale, equatorial gravity waves, Rossby gravity waves, and Kelvin waves, as well as internal gravity waves, all shown in orange. And then there are, in the mid-latitudes, there are planetary scale Rossby waves, and they are all going upwards from the lower atmosphere into the stratosphere and mesosphere, and influencing the background flow. So the background flow here is shown as westerly flow and easterly flow to the east and to the west. Yes, so and then there are also vortex Rossby waves, like smaller scale waves in the context of cyclones and hurricanes. So now I as a mathematician, as I mentioned, I usually have to use simplified models in order to be able to do mathematical analyses, and get approximate solutions, which I can then use to validate numerical computations. Now, the problem or the issue with gravity waves is that because they are relatively small scale, on the so-called mesoscale, they are not always resolved completely by general circulation models. If the grid spacing on a large-scale climate or weather prediction model is a certain order of magnitude, which happens to be on the order of magnitude or larger or close to the order of magnitude of the gravity wave wavelengths, and also that maybe the time steps in the model are also on the order of magnitude of the evolution of the gravity waves, then the waves would not be properly resolved by the model. The larger scale waves generally, almost always are, modeled by any good climate or weather prediction model. For many decades, gravity waves could not be resolved and needed to be represented, artificially added to the model in the form of a parametrization scheme. Now, over the past 2 decades or so, many models can resolve gravity waves, but still not always completely. So we need to have information, as much information as we can about gravity waves based on simplified mathematical models. And so that's where my type of research comes in. So analytical studies can provide missing information, and which would also help us to properly model the gravity waves. And as I mentioned, we can make different simplifications. One would be using 2D rectangular geometry instead of spherical coordinates. So like in this picture, instead of spherical coordinates, we've got a horizontal variable and a vertical variable in 2D. So when I use 2D rectangular coordinates, I'll use X to represent the variable going from west to east, and Y to represent the north-south or the south-to-north variable, and Z to represent altitude, which will be the coordinate pointing outwards from the surface of the Earth, which from our perspective, standing on the Earth, will mean going upwards. Now, we can also make approximations to the equation, such as the Boussinesq approximation, where instead of considering a compressible flow, we consider the density to be constant everywhere, except in the terms involving the acceleration due to gravity, where we need to retain it. Otherwise, we wouldn't have gravitational effects. Or a better approximation would be the anelastic approximation, where we approximate the density by a function of the altitude Z in the continuity equation, the conservation of mass equation, and that simplifies our equation, simplifies our equations, and allows us the equations to be more tractable to analyses and so on. Also filters out other effects such as acoustic waves, which could interfere with our numerical computations. Smaller scale waves could interfere with our numerical computations, but by making these such a simplification, we are able to filter them out and just focus on the gravity waves. Also, we might use perturbation method, where we say the total of any fluid quantity is the sum of the background quantity and the perturbation, and then consider that we assume that we know what the background flow is, and we add to it the perturbation, the oscillation on top of the background flow, and then we solve for that, knowing the background flow quantities. I will be talking about situations where the background flow is a shear flow. So, for example, the velocity, horizontal velocity of the background flow depends on the altitude. So instead of considering it to be just constant, it changes depending on the level, the altitude that we are measuring it. So we'll put a bar like this, an over bar on the background flow quantities. Also the same for the background density and so on. And then for the perturbation, we'll assume that we are, or we'll consider a situation where we have non-dimensionalized our equations, written the equations in non-dimensional form so that we can make comparisons between different terms and different effects in the equations and compare them without having to take into account the units of measurement. So when we non-dimensionalize the equations, then we will have some parameters that will measure the relative importance of some terms to others. So one way to do that will be to introduce the perturbation as being some parameter epsilon times the function, non-dimensional function, which would be taken to be order 1. So by doing that, in this case, epsilon will give a measure of the relative magnitude of the perturbation quantity to the background flow, with the corresponding background flow quantity. In the context of waves, our perturbation, if it's meant to be a gravity wave, it would be oscillatory in the spatial variables and in time as well. So periodic, definitely in the x direction. And if we are thinking of a periodic wave, then it means we can represent it in terms of Fourier modes, like some amplitude times e to the I kx. Of course, everything has to be real, but we use complex exponentials with the understanding that every time I write this, I'm adding the complex conjugate to get a real function, like e to the I kx plus the complex conjugate being cosine kx. So if we are using Fourier modes, then it means that we can use the methods of Fourier analysis in our analytical work and also use them for numerics, like taking Fourier transforms, using FFTs, fast Fourier transforms for computations and so on. So epsilon is a non-dimensional parameter. It gives the amplitude of the wave relative to the background flow. In general, the wave is of relatively small amplitude compared with the background flow, just like in cases like here where we have waves on the surface of our water and the amplitude of the wave is small relative to the background, relative to the depth of the flow. So epsilon will be taken to be small for the purpose of asymptotics and even for numerics. And in the limit as epsilon goes to 0, we'll generally have linear equations, which will act as the first approximation to our problem. So our problem would be to study the evolution of the flow over time, of the wave perturbation over time. And from the perspective of hydrodynamic stability theory, the question is that if the fluid flow is at rest with the basic flow only, and then we apply some force that generates a perturbation, we want to know what happens as time evolves. Does the perturbation eventually die out? Does its amplitude go to 0 as t goes to infinity? Or at least does it stay constant? Or at least remain finite by a function that's bounded by can be bounded by a constant as t goes to infinity. If so, then we would say we are in a stable situation. Or on the other hand, does the perturbation continue to grow indefinitely with time, meaning that the amplitude goes to infinity as t goes to infinity and cannot be bounded? In that case, we would say it's unstable. And so stability and instability are, in this context, are analogous to the concept of stability in systems of differential equations or stability of numerical methods. There are many different things called stability in applied math, which are all kind of analogous, but with slightly different definitions. Another issue we'll look at is what happens as the wave goes up, as altitude, which I'm calling z, the variable I'm calling z, increases. So the background density decreases with altitude, and the temperature, or background temperature, is also changes, and as a result, the wave amplitude increases with altitude. So eventually, if the wave amplitude gets large enough, it may get to a point where the wave would break. What would happen if, in this formulation, the F here is no longer order 1, but it's got so large that it's now order epsilon to the -1, 1 over epsilon. Then that would mean that the perturbation is now the same order of magnitude as the background. And our mathematical analysis based on epsilon being small would no longer work. We would have to do some kind of multiple scale matching of some sort to look at a different parameter regime and maybe match to the original regime where we did have epsilon being small. So that's another concept to think about. I mentioned that the wave can be represented in the form of Fourier modes. So the normal, what we call the normal mode representation, is where we represent our function in the form e to the I k x minus ct, where k is then the wave number, horizontal or x wave number, and c is the phase speed. In this case, kc would be the wave frequency. As I mentioned, taking the real part or adding the complex conjugate gives us our real function, in this case, cosine of kx minus ct. So to investigate stability, we could consider the C to be complex. That's a usual idea from hydrodynamic stability theory, and say the complex phase speed, real part plus I times the imaginary part. Putting that in here means that we will have e to the I k x minus real part of c times t times e to the c imaginary part of c times t. So this exponential with a real exponent obviously could grow or decay with time. So we'd have an oscillatory part, but we'd have a factor that's making the wave amplitude either increase or decrease with time or stay constant, depending on the value of c. Depending on the sign of C. So the traditional idea in hydrodynamic stability theory, formulating the problem in terms of normal mode, says that if Ci is less than or equal to 0, then we have stability. If it's positive, then we have an instability where this would increase. And so that idea is behind what we do in our gravity wave formulation. So going back to our equations, these are the equations I would get if I took my original equations and made the Boussinesq approximation with the simplification where to allow us to simplify and model the compressibility by considering the density to be constant in some terms in the equation. And so this here, the psi and rho are two independent variables to be determined. Two dependent variables to be determined. And we've got a 2D formulation with x and z. The functions shown in orange are the background flow quantities like u bar and rho bar and so on. And so a normal mode solution would be to say we have a wave amplitude multiplying this normal mode form. And if we plug that in, the wave amplitude is supposed to depend on altitude. So when we plug it in, then we get an ODE for the wave amplitude. And this is a well-known equation called the Taylor-Goldstein equation, which has been studied for many decades since the first brought forward like more than 60 years ago. So we have an ODE in this case, second order ODE, which we get by combining these two equations, differentiate this equation, differentiate that equation in such a way that when we subtract one from the other, we cancel out to the density wherever it appears, and we end up with an equation just for the stream function. I should have mentioned this is the stream function. The stream function written in this form. So we have an amplitude equation. And this Taylor-Goldstein equation is a second order ODE. This quantity n is what we call the buoyancy frequency. N squared is minus g over rho bar times the d rho bar dz. And it has to be positive in order to have gravity wave solutions, because if it's negative, then this whole quantity here, coefficient, might be negative, and we would just have waves that decay or grow with z. but in order to have oscillations in Z, we need n squared to be positive, which would make sense if the density is decreasing with Z, because there's a negative sign here. So that's the buoyancy frequency, or Brunt-Weisser frequency. And so if we look at this equation, we can also define the Richardson number, which is the ratio of the extent of the density stratification measured by the n squared to the vertical shear, which is measured by the du dz. And there's a theorem, well-known theorem, the Miles-Howard theorem, that says that the necessary condition for instability is that the Richardson number, which is this ratio, should be less than 1/4, 0.25, somewhere in the flow. And meaning that if it's greater than 1/4, then we can have then we are guaranteed stability of our background flow. But on the other hand, if it's negative, then we expect things to be unstable. And that's a convective instability that we would get. That would mean n squared would have to be negative, which would mean the density increasing instead of decreasing. And so I'm interested in a phenomenon called the critical layer, a critical level, which also gives rise to some types of instability. So looking at that equation, the Taylor-Goldstein equation, we see that if U bar, which is a function of Z, happens to be equal to C at some level, then at some altitude Z, which I'll call ZC, then the equation, the ODE, would be singular. Now, provided that U bar is an analytic function of Z, with a convergent power series expansion, this would be a regular singular point. And so we can use the method of Frobenius or whatever method we want to find the solutions of this equation. And at leading order, we have a solution that looks like this. It's Z minus ZC to the power half plus minus I times some constant. No, to the power I, no, Z minus ZC to the power half plus or minus I times a constant, which is the square root of the Richardson number minus 1/4. Now, rewriting that to put the complex exponent into this form, to write it as a complex exponential, we see that there is a logarithm, there would be a logarithmic phase shift across the critical level, because if we take the log of Z minus ZC, if there is in the part of the domain where Z is less than ZC, this would be negative. So when we take the log, we'd have the log of the absolute value plus or minus I times pi, the argument of the complex function. And it could be positive or negative. There is a way, if going into the complex plane, taking a Laplace transform, considering a time-dependent equation, taking the Laplace transform and doing going around the branch point, and we can use that to determine the sign of the phase shift here, the sign of the argument of the complex number, and also the sign here, plus or minus. One of the two waves will be upward propagating and the other one would be downward propagating, depending on whether we take the plus sign or the minus sign, upward group velocity or downward group velocity. So based on that, we can determine the correct sign to use here and there. And when we do that, say in this case, if the mean flow looks like this, then U bar is negative down here. So to have an upward wave, we'd have to take the plus sign here. And then also the derivative is positive here. And that tells us the branch of the complex log to use. And it turns out it has to be negative. So if this is positive and this is negative, then when we plug this in here, we end up with below the critical level having a factor of e to the something positive, meaning that this place down here will be larger. The solution will be larger, whereas here it will be smaller. So there'll be the wave amplitude going from below the critical level to above will be reduced by a factor of e to the minus something which is positive. So if I draw the graph, which means there's a discontinuity in the wave amplitude. So when I draw the graph, plot the graph of the exact solution, it looks like this in 2D. If I multiply this by e to the ikx and then draw a contour plot, or if I draw the graph as a function of z, it looks like that. So the wave, we have an oscillation below the critical level, and then above the critical level, it's multiplied by this constant, which is small. So that means it looks like it's zero above the critical level. So there's a critical level, wave amplitude being reduced below the critical level, being reduced above the critical level. And that results in practice, when we go back to our original problem with nonlinearity and viscosity and time dependence, oops, missed a letter here, then what we find is that as a result of the wave amplitude being decreased as we cross the critical level, there is a mean flow acceleration. What happens physically is that there is a transfer of momentum and energy from the waves to the mean flow, from the wave scale to the scale of the mean flow, cascade of energy from the smaller scales with the wave scale of the wave to the large scale mean flow. And that's the result as a result of the wave absorption, and that can lead to wave breaking, turbulence, and so on. And then there is also the issue of the wave amplitude increasing and getting to a point, increasing with height, with altitude, and getting to the point where there can be an instability. So that's a static instability. So all those different things have to be taken into account. So now in my modeling, I've gone back to my original equations, and I've made an elastic approximation here. So the equations are more complicated. Now we have the nonlinear terms. We've retained the viscous term, the heat conduction term, a forcing term that's used for generating the waves. And this has been written in a stream function, a density weighted stream function, written in terms of U and W, the velocity components, and then psi is a vorticity of the waves. So all these are the wave components, and the quantities with the bars on top are the background flow that we know. So there are different ways we can generate gravity waves. We can do so by adding a non-homogeneous term to the temperature equation. Theta is the temperature and psi is the vorticity. So by having a non-homogeneous forcing term in the temperature equation, we can use that to generate waves. I'll show you in the next slide what that might look like. And we can think of that as some thermal forcing, some place in the atmosphere where there's some heating, that's localized heating that generates the gravity waves, as might result in a situation with convection in the atmosphere. Or we could think of it as a problem in some domain, and the waves are being generated by the lower boundary and then propagating upwards. So we might have an oscillatory lower boundary and generating waves which go up to their critical level, like what we did here in the exact solution, where the waves were going up. And so in the last time I gave a talk here, I talked about some types of waves, and I talked about numerical solutions, but didn't mention the numerical methods. And a few people were asking me about numerical methods afterwards. So this time I made a slide just to talk about the numerical methods briefly. So we have, in these types of wave simulations, what I often find convenient to use are Fourier methods for the reasons I just gave. They are oscillatory, the waves being oscillatory in horizontal space. So let's say x goes from 0 to 2 pi in non-dimensional quantities. So I discretize my x, and then I take a discrete Fourier transform of each term in the equations. The transforms have a hat on top. So f hat for each quantity is the transform of the function f. Kappa is my Fourier coefficient Fourier variable, and then I get my discretized equations. I do a pseudo-spectral approximation where I have, for the nonlinear terms, I take the Fourier transform of the product to invert back into real space, then multiply the nonlinear terms, then take the Fourier transform of the product. And so that's a pseudo-spectral approximation. Then we can discretize the other variable z and discretize time using my preferred method of discretization, finite difference, finite elements, whatever method we want to use, and then solve these two equations by time matching. This is the t derivative here The derivatives are denoted with subscripts here. Solve by time marching, and then at each time level we invert invert a matrix to solve for the stream function in terms of the vorticity that we computed at the new time level, and then we compute the nonlinear terms, and then we go on to the next time level. So that's the general idea behind the numerics for this type of problem. So that's the approach I generally take with doing numerical simulations. Now I'm just going to show a couple of slides showing some results I obtained and talk about how we might interpret them from solving these equations. In the first case, we have a situation where we have a forcing term like this, which is generating the waves in our two-dimensional domain. And the forcing term I'm going to show is of the form oscillatory in x and t, but as a function of z, it's a Gaussian function, like e to the minus b, some constant, times z minus some level zc all squared. So that's a Gaussian function centered at z0, and the b determines how fast or slowly it changes with altitude. So we have a function like this as our f centered at this level, which is our z0, and that's our non-homogeneous term. And then the background flow, I've set it to like what I had in my earlier picture with, so here this is 0, u bar going from -1 to 1. And so at this level, z equal to 5, u bar is equal to 0. And that's where our critical level is. So we expect that if we generate waves in the lower part of the domain, when they go up and get to the critical level, we will observe critical level phenomena. We are solving the full equations with nonlinearity and everything, but so there's no singular point in our equations, but we do have some wave phenomena occurring around the critical level, even though there is no actual singularity. So in 2D, as a 2D picture, x and z, we have the thermal forcing term looks like that, these blue contours, this profile, but it's multiplied by an oscillatory function of x. And so with the thermal forcing being imposed here, we generate waves that go up. But when they get to the critical level, they've basically disappeared, vanished completely, or we don't hardly see anything above the critical level in the numerical simulations. This is the temperature, wave temperature profile as a contour plot, and this is the stream function. And we see that there's stuff going on. Something is happening around the critical level. We can't really see it because the contour levels are so close together. But if we zoom in, then we see we've got these closed contours all directly centered at the critical level of 5. So this is zooming in to take a narrower slice and going from maybe 4.8 to 5.2 around the critical level. And then the stream function too goes up, almost completely disappears. And as a result of these changes, as a result of these interactions, there is a change in the mean flow at the critical level and also at the forcing level. And that change in the mean flow comes about because if we plot we can see it if we plot the Fourier spectrum of the wave perturbation. So this is the temperature and the stream function in Fourier space. So since the wave was e to the I, kx, and k is 2 in this picture. That's why we have two wavelengths in this picture from 0 to 2 pi. The wave spectrum is centered at ±2, -2, +2. But as time goes on, other higher wave numbers develop, higher wave number components develop, as well as a mean flow term, which corresponds to the 0 wave number, k equal to 0. And the same thing with the stream function. This large, here the 0 wave number is even larger than the 0 wave number component is larger than the original waves plus and minus 2. And if we plot the contours of the temperature, total temperature, we have a contour plot that looks like this, zooming in on the critical level, which is here at 5. And here, you can probably just see some gray curve here, gray region here, and there, And there, that's the Richardson number, the regions where the Richardson number is negative, which corresponds to convective kind of instabilities. As I mentioned, the Richardson number being negative means we expect some instabilities, and that's where the density and temperature contours are overturning, as we see here. So I'll just show one more picture and then I'll conclude my talk. So this is a situation that shows how different effects that can result from imposing a thermal forcing in the adding a thermal forcing to our configuration and generating gravity waves. And another way to generate gravity waves would be, as I mentioned, forcing the waves from below as a lower boundary condition. We could have, for example, a wave packet oscillating like that. Or we could have, so here we have a Gaussian function of x multiplying e to the ikx. So there's an oscillation, but the amplitude is slowly varying in the x direction. Or we can have k equal to 0, where we just have e to the minus mu squared x squared. So just the Gaussian profile. This would correspond to the case like what we had right at the beginning, or what we had here in this picture, where we had like an isolated mountain generating waves. Let's go back here. So let's look at this case where we have this as our lower boundary condition. And so there's no oscillation in the x direction, but in spite of that, we still get a wave-like solution. Oscillation, there's no oscillation in the x direction. It's like there's an isolated mountain down here generating the waves, topographic type waves, but there's an oscillation in the vertical direction, as you can see, red, blue, and so on. But when we get to the critical level, again, the waves are completely absorbed, almost completely absorbed. And in this case, there are other phenomena taking place. There's some horizontal flux of momentum and energy going outwards as well in the direction of the group velocity of the waves, so mostly going out in this direction. So, and then there's wave phenomena, critical layer phenomena taking place here, which I don't have time to get into the details, but this was part of a study I did with a student in a number of years ago. And this one here is a more recent study that I did, which just appeared in Applied Math Modeling. So let's just go to the concluding remarks. So in the studies like what I just showed, I gave 2 examples of studies that make use of all the theory that I described in the first part of the talk. Analyses which allow us to determine what is going on and give predictions as to what we might expect from the numerics. But based on simplified models. The analysis can be continued beyond the linear analysis by putting back in the nonlinear terms and doing a weakly nonlinear kind of analysis, maybe a late time solution, multiple scale solutions, asymptotic matching and all that. And then we do numerics, and the numerics are in agreement with what we expected from the analyses. With the waves going up, interacting at the critical level, and transferring energy to the background flow. And these types of analyses can help give us insight to improve the representation of unresolved gravity waves in large-scale models. And I'll just conclude by saying that the last time I spoke here, I talked about vortex Rossby waves, which showed similar type of behavior. Mathematically, the problem is similar to what I just talked about here, but physically, it's a completely different context. And there are also situations with large-scale Rossby waves. I've recently looked at a case with Rossby waves interacting with gravity waves on 2 different scales, but because they both interact with the mean flow, they can end up being some interaction between them. And even gravity waves, when they go up into the upper atmosphere and they are under the influence of ion drag forces, then that introduces other phenomena. So, but I'll end here. So thank you, all of you, both in Zoom world and in the lecture room, for your attention. And of course, I'm ready to take questions.
Yeah, thank you so much for such an inspiring, that talk, when we look at it, we like, some of my students here can recognize some other stuff, and I'm hoping they'll give you tougher questions.
Okay, good.
Yeah, I'm hoping, do we have any questions online? Okay, we were hoping we will get some questions online. Do we have any questions on the floor here? Yeah, you can start.
So I'd like to know, I've got two questions. So why did she choose the Bosnistic approximation?
Can you hear her?
So why did I? Oh wait. So let me just stop the
Why
share.
did you choose the Bosniak approximation?
Oh, okay. Yeah. So the for the Boussinesq approximation, I used it just for the purpose of explaining the idea of the critical level. So the Boussinesq, if you make the Boussinesq approximation, then you get this Taylor-Goldstein equation in a very simple form, in a relatively simple form, and it's easier for me to explain, just to show you where the singularity comes about and so on. Now, if I use the different approximation, fuller version, like let's say the anelastic approximation, I would get a similar equation, but there'll be some additional terms. So in this slide, the only reason I used Boussinesq was just for the purpose of making the equations look simple for my talk, to explain what the idea of the critical level. Now, in the numerical solutions, this is not the Boussinesq, but this is the anelastic approximation, which includes, it's a more realistic formulation, more realistic approximation, still not the full equations. And the reason to still use an approximation is if I use the full compressible equations, then there may be other effects like sound waves that would appear in my numerics, which I don't want to look at. So making this approximation filters out the smaller scale sound waves so I can focus on the gravity waves. So I can use the anelastic approximation in the numerics, but just for the purpose of explaining a simpler problem, I used Boussinesq in the first few slides. We can always choose what approximation we want to use, depending on how simple we need to make the problem or how much more realistic we would want it to be.
So I was thinking also about the moon and how the moon affects, the tides in the ocean, and also the moon has a certain gravity pull towards the Earth. So will you eventually get to a point where you include that in your calculation for what's happening in the ocean? Yeah. Or
yeah. So not in this calculation, but the tides. The moon, the effect of the moon affects not just the ocean, but also the atmosphere, in the sense that there are tides in the atmosphere, and the tides are actually gravity waves like what I've talked about here, but on a different scale. So we can study the tides in the atmosphere in a very similar way. Mathematically, it would be similar to what we did here. They would be just another type of gravity wave to study, included among the different types of waves I mentioned. But here I'm focusing on gravity waves, which are on a smaller scale and are not directly affected by that. Now, tides in the ocean could also affect the gravity waves if we are considering the effect in the ocean and the influence that it has on the atmosphere above. So we could have like a two-layer model where we are studying the waves in the ocean, effects in the ocean that result in surface waves. But the surface waves are the interface between the ocean and the atmosphere. So those waves affect the waves that are in the atmosphere, the internal gravity waves, which are in the atmosphere. So yes, that's another thing we can look at. There are many different things going on. And in general, for a mathematical study, we isolate the things we want to study and focus on them. But we can include the tides in the atmosphere or tides in the ocean as well.
Yeah, we have another question.
Yeah.
Hello, Prof.
Yeah.
Thank you for the presentation. Please, can you go to slide 14?
14, okay.
Yes.
Yeah.
Okay. So where we have the log of Z minus ZC.
Yeah.
So we have, so it gives us the log of the modulus of that.
Yeah.
Generally, I would expect to see maybe plus or minus I times the argument of Z minus ZC. There's a reason why that becomes pi.
Oh, it's because it's so the pi, the reason why it's plus or minus pi, why the argument is plus or minus pi is because I'm considering that this log that appears here. Can you see my annotations when I'm writing on the screen? Yeah. So I'm taking this log, here, and considering that when Z is greater than ZC, then you get to take the log and it's real. But when Z, so that's where the argument is 0, the angle is 0. But when Z is less than ZC, then now it's log of a negative number. So the log of the negative number in the complex plane, the log of -1 if we are in the complex plane is this, and so it can either be considered as pi or minus pi. So I'm just taking taking the log of -1. It can be pi or it can be minus pi. So now if we go into the complex plane and we want to determine which one is it plus pi or minus pi, then in the complex plane we would need to do a contour integration around there will be a branch cut around this line, and we can do a contour integration around this to determine which approach we want to take, whether we want to go on the positive side or the negative side. But in order to do that, we go back to the original problem, which had time dependence, the t derivatives, and take a Laplace transform. That's one way to do it. Take a Laplace transform. Then when we are inverting the Laplace transform, we are in the complex plane, and then we do a branch contour integration, and that tells us which branch to pick. And it turns out that the branch to pick depends on the sign of this. And if this is positive, then it turns out the branch we want is the negative one. And so that's why we have ended up with negative. But if it was a mean flow profile that went like this, for example, then we would have the derivative would have been negative, and it would turn out that the branch that we would have had to pick the branch with the plus sign. So there's a lot more going on here, but it's a very straightforward procedure of contour integration to determine the sign.
Okay, I think we have another question online.
Okay. Is it in the? Is there a question in? Okay, let me just. Is it in the chat?
No, Pando has raised a hand.
Okay, yeah, okay, yeah. So I'll go ahead with your question.
You can unmute.
Yeah, I'm trying to. Are you in the?
Online.
Yeah. Okay, go ahead with your question, please. You can. Yeah. Yes, I can.
Can you hear me?
Yes.
I have a quick question. If one looks at synoptic scaled Rossby waves in the real atmosphere, the critical layer would be found at in the subtropics, or more or less, where we have our wave breaking and wave reflection and so on in the real atmosphere for synoptic scale waves. For gravity waves, breaking waves in the troposphere or lower stratosphere or something would be important for aviation. So the question I have is, where is the critical layer for such waves in the real atmosphere approximately?
So if we look at let's see, maybe let me just look at this. Go back to this picture. So if we look at a situation like this, if we look at a situation like a configuration like this, where the gravity waves are being generated, maybe convection is generating the gravity waves and they are going up. So there might be topographic waves being generated in the lower, in the troposphere, going up into the stratosphere, and the critical levels for those waves might be somewhere in the stratosphere, in the upper stratosphere, so the middle atmosphere, so somewhere in the stratosphere. But then there are also internal gravity waves generated by convection and other effects in say around the tropopause, let's say upper troposphere, lower stratosphere, which go up and also have critical levels. So most of the gravity wave critical levels would generally be somewhere in the stratosphere, but then there are some waves which might go beyond the stratosphere and go up into the mesosphere. So the generation, they may be generated usually in the troposphere and lower stratosphere, and then the critical levels would be in the mid stratosphere and above. And so those turn out to be really important because the wave breaking at the critical level and the wave saturation can sometimes result in turbulence. And then that's why we have turbulence over mountains when we fly over mountains. So as you mentioned, very important for aviation.
Mm-hmm. Thank you very much.
Yeah. Thanks.
I think there's another question in the chat.
Oh, okay, in the chat. So let me just check out the chat. Okay. Okay, so let me see the question. So you mentioned that the waves are propagating upwards until they reach the critical layer. Then we assume a solution with x minus ct. So the question is, where is the vertical propagation coming from? Or the waves propagating horizontally, but the amplitude changes with height. Yeah, okay, so the question is, I talked about waves of the form as a function of x minus ct. And so the question is, I didn't mention z in that. So why is there vertical propagation? And so let me just go back to the equations to clarify. So let me just... Yeah, so in the... when I did this, I mentioned this. This was just an explanation of the idea of the normal modes, and I was only just talking about the component oscillation in x and t. But in fact, the waves that we are talking about, even in their simplest form, they always have a z component, a z dependence. So the vertical coordinate, the altitude is z here. So even in their simplest form, the wave function is oscillating in x and t with an amplitude that depends on z. And now we are trying to determine how the wave changes with respect to altitude. So why is there propagation? Why is there an oscillation? Because if we take mathematically, we can understand that if we take this and plug it into the equations, and we get an equation like this, this is the simplest version where I've made the Boussinesq approximation, but we could do it for a more realistic version as well. We end up with an equation that looks like this. And then if this is positive, we have like second derivative of phi with respect to z plus some positive quantity multiplying phi. And so therefore the solutions, if we have this, if you look at an equation like this, plus something positive times phi equals 0, and let's say this is called, I call this B. So I'll have the solutions, if this is positive, then the solutions would be e to the plus minus I, and then we take the square root of this times z. So we are getting an oscillatory solution just from the nature of the equations. The equations lead to an oscillatory solution. Now, if this was negative, or if the whole thing, and the whole thing here was negative, then we'd have a situation where we have the second derivative minus something with something negative. Then we'd have solutions that are not oscillating. They would be like plus minus square root of b times z. So in order to have gravity waves, we need to have this to be positive, and then we automatically get an oscillation in z. Now, I'm explaining this from a mathematical perspective right now, just looking at an ordinary differential equation. But that's true even if we go to the full equations. There is an oscillation in z, provided the n squared is positive, and this whole thing here is positive. Right? So the oscillation in z in altitude is coming about from the nature of the equations which model the wave propagation. And that's true in practice based on the physics of what's going on. This is the mathematical understanding. So in the end, when I do, when I go back, this was just the simplified, linearized, simplified problem. But in practice, when I'm doing an actual numerical solution, these quantities here are all functions of x, z, and t. So the function variables here are psi and psi and theta. the temperature, the stream function, and the vorticity. And they are all functions of x, z, and t. The oscillation in x is introduced into the problem by either the thermal forcing term or the boundary condition. And then we get, as a result of that, we get an oscillation in z, which we are, which we are seeing here in the figures, like this. The oscillation in z comes about here. This would be like positive, and then negative, and then positive and negative. Okay, so that's the oscillation in z that comes about from the forcing.
All right. Yeah, I see there's another question, Prof. In the chat.
Okay.
Is it possible for the wave to break before reaching the critical layer? How can we represent this wave breaking then?
Yeah, so what are some other phenomena that might make the waves break? So the main things that might make waves break would be the critical layer interaction and the static instability, or the wave saturation and breaking that occurs because, let's say you've got a wave going up like this. In the Boussinesq approximation, the wave amplitude would be kind of always finite. But if you have a case where the density and temperature are changing with time, the wave amplitude may be going like this. So imagine you have a wave that's going up like this in the z direction. And eventually it gets to a point where its amplitude is so large relative to the background flow that the mathematical model breaks down, because now the perturbation is the same order as the background flow. What would that mean? What would be the physical interpretation of that? That's equivalent to where if you have surface waves, like on the ocean surface at the beach, and they're going like this, and eventually the amplitude gets larger and they are dispersive, and then eventually you get a situation where the waves overturn. So when the waves overturn, then they might break. So we can have wave breaking as a result of just due to the fact that the amplitude is getting larger. When wave amplitudes get larger, they tend to break. But also when the waves get to a critical level, they tend to break. So there may be some level, which I've called Z break here, where the waves are breaking because the amplitude got large. But there may also be a level which is ZC, which is the critical level. So the question is, which one comes first? If the wave amplitude is increasing fast enough, but there's no critical level between the ground or wherever the waves are coming from and the breaking level, then it may be that the waves will break and never get to the critical level. But another possibility would be if the critical level is below, then the waves get there and are either absorbed completely, or they break, or they are reflected, or something happens and they never get to the breaking level. So in practice, there'll be a breaking level and a critical level, and which one is below and which one is above. That will determine what happens. And this is observed in the real atmosphere as well, although I'm explaining it from kind of the mathematical perspective.
All right. No, thank you so much. I don't know, are there any other questions? Our time is almost up. It's actually up.
Yeah.
I'm going to allow them because they're students.
Yeah, yeah. They have to go to class. Yeah.
Yes.
So I've got one more question. Prof does something interesting with the analysis. She introduces nodes in the system, and then she introduces...
Oh, wait. Excuse me. Can you please start the question again?
Yes, I was also asking that.
So, Prof, you do something interesting in your analysis. You start off with nodes, you introduce nodes, and then you go into space and you go back into the real space. Is that because our waves are oscillatory and we have a complex plane coming into play? So if our solutions didn't have a complex form, there wouldn't be a need for Fourier series.
Oh yeah. So you mean like where does the Fourier series? Why do I introduce a Fourier series? You mean like doing this? Is this what you are? Yeah. So why do I do like stuff like this, where we have e to the plus or minus whatever I wave number or Fourier coefficient x? So why am I doing stuff like this? Is that what you mean?
That's why you're introducing the Fourier series.
Okay. Yeah. So I could go take my original equations, which were in X space. So my PDEs are in X, and Z and time. So maybe there's a time. So because I'm doing a 2D thing. Now I could do 3D plus three spatial variables and time, but I'm doing 2D and time. So my PDEs are in terms of X, Z, X and Z and T derivatives. So I could discretize the X using whatever finite differences or finite elements, whatever method in X. Now I'm choosing to use Fourier method in X because of the fact that I'm imposing a wave that's oscillatory in X. The oscillation in Z is not imposed. That comes about from the equations, as I just explained in answer to the other question. But the X oscillation is what I am imposing. So because I know I'm putting this in, typically when you are solving a problem where you know that you are putting in an oscillation of this form, then the Fourier methods are just better numerically. We can do a comparison of different methods, and for several different reasons, Fourier methods are more efficient and more accurate. Because of you choose your method based on the formulation of your problem. So knowing that I've put in this as my boundary condition and I'm generating a wave in terms of this. If I did a linear solution, I would just have that one wave number, let's say e to the 2ix, plus the complex conjugate e to the minus 2ix. So I'm putting a cosine down here as my boundary condition. So I know I have wave numbers k equal to 2 and k equals minus 2. And if it was a linear problem, I would only have those two wave numbers. But because it's nonlinear and we have terms that are multiplied together like this, we'll have this one times that will give me e to the 0. This one times itself will give me e to the 4ix. And then we'll also have minus 4ix and so on. So we're generating higher wave numbers and the 0 wave number component. So knowing that I'm going to be generating those, the natural best method to use is a Fourier method which models each of those modes, those wave numbers. And so I do that and I get a solution in Fourier space that looks like that for each wave number. Now, if I had a continuous spectrum, then instead of a Fourier sum, I would have like a Fourier transform, like a Fourier integral, something like this. And then it would be like an integral. And in that case, I could approximate this Fourier integral by a sum and then still use the DFT, the discrete Fourier transform. So it's basically choosing a method that works best for the particular type of problem.
No, I don't see any other questions from the chat, but we enjoyed this talk, and I think the students, they're probably going to be asking me more questions.
Oh, okay. Okay, yeah. So if anyone has any questions or you want specific questions and you want any information from me, you are free to email me. I can also send you copies of some of the papers that I mentioned and others where we go into more detail, like say the argument about how to pick do the contour integration and pick the correct branch and the group velocity and the numerical methods and all that. So I'm happy to send any other information to answer questions in more detail.
Expect my email there.
Yeah, hopefully one day I'll be able to visit you guys there in South. Yeah, then I can give you more information.
Thank you. All right, now let's take our speaker. Thank you so much. Thank you so much.
Yeah, well, thanks for inviting me.
We appreciate it of your work. Because similar to some of the work that we do here, so we want to learn and engage with other people.
Yeah, that's good. Good to know. I'm glad that the students enjoy, especially, were able to attend the presentation. And if some of you are doing related work, you're always free to email me if you have questions about some of the things you are doing. I'm studying many different types of waves. But from my point of view as an applied mathematician, the mathematics is similar, even though the problems are very different. And that's the power of using mathematics to study problems in physics.
Continue talking, because I keep on telling them the same thing.
Yeah, okay, yeah, good, okay, yeah, that's the point. Yeah, as a mathematician, once you've taken your physical problem and discretized it or represented it mathematically, then from a mathematical and non-dimensionalized things, then from a mathematical problem, it becomes just, okay, this parameter is small, this one is large, this term is doing this, these are the Fourier modes, and you don't even need to think about the physics until you've got some mathematical insight. Then you go back to the physics and say, okay, did the mathematics I do even make sense in reality? And then you have to try and connect them again. So that's the idea.
All right. No, thank you so much once again. And we shall